So good morning, everyone. Welcome back to Math 115. This is going to be our second review session. So the first review session was yesterday during office hours. I will post the recording to my YouTube channel so that you can review things from this. The way I'm going to try to do review is I'm going to try to not repeat things from review session to review session. So if you ask a question and I've already answered that in another review session, I will say, I talked about that in office hours on Tuesday. Go watch the YouTube video. It's like halfway through or something like that, and I'll give you some guidance there. And then, yeah, I'm going to have another review session tomorrow in class in the morning, and another review session tomorrow afternoon during office hours. Tons and tons and tons and tons of review options. If you can't make it to office hours, don't worry. I'm recording them and posting them to YouTube. What I thought we would do today is, well, first of all, I want to give precedence to, no, not precedence. Precedence? Priority? Maybe I'm thinking priority. Anyways, I want to give priority to students who have questions. So if you have any questions, then we'll talk about those first. Otherwise, what I thought I'd do is go through the homeworks and give you a quick, listing of the topics, and what I would hope you would do during that time is, okay, seriously? Here we go. What I hope you would do during that time is listen to me saying all of the different things that we did, and if I say something like completing the square, where you're like, oh yeah, I do remember learning that, but I don't remember how to do it, you write it down, completing the square, and then that's one of the things that you know you need to study, and you know exactly which section it's in, etc., right? So before we do that, anyone have a problem that they want to discuss or a topic that they want to discuss? Yeah.
There was one in the homework that was like the sum and difference formulas, but it was like with tangent. I did not know how to do.
Okay, what was it? It was like, can you?
Probably find it.
Yeah, you work on finding that. In the meantime, any other problems? Okay, let's see. Maybe I can pull it up. It was the most recent homework, 5.5?
I think it was 5.3.
5.3. Okay. Let's see if I can preview. It's probably going to make me log in again. Okay, yeah. Okay, let's just go ahead and rip that Band-Aid off. Okay, 5.3, preview. I think I know the problem that you're talking about.
5.2 actually.
It's 5.2? Okay, so 5.2. Do you know what number it is?
I think one of the later ones.
Okay. Let's try 15. No. 16? That might have been too far. 14. Here we go. Sum or difference formula to find tangent of 7 pi over 12. Okay, let's think about that for a second. I think I know how to do that one. Okay, so let me put it back on the screen so you can all see, full screen mode, and allow me to just copy in these sum and difference formulas. Oh, look at that, they're right there. And I'm going to use two of them here, actually. So you should probably put these on your formula sheet, by the way. Copy, and review notes, paste. Okay, so here we have our sum and difference formulas. And let's see how these are going to help us to do this one. So the thing is, we didn't learn any sum and difference formulas for tangent, right? And that's why you probably felt like, this is so unfair. I hate Tom. I want him to die. No, just kidding. You didn't think that, but you did think that this is unfair. But I claim it's not unfair because Tangent, you know an identity which relates tangent to sine and cosine. What is it? Tangent of theta is equal to what? Sine of theta over cosine of theta. Okay? So, if you know how to do sine of 7 pi over 12 using, which one? This identity, and you know how to do cosine of 7 pi over 12 using this identity, then you're going to get where you need to go. Is the strategy clear, Andrew? Okay. I think if you had that, probably you would have been able to do it, right? Okay, so let's do it anyways. So sine of 7 pi over 12 divided by cosine of 7 pi over 12. Now comes the hard part of the sum and difference problems, which is to express this angle, 7 pi over 12, as a sum or difference of angles which I know how to do. So what we're trying to do here, okay, is use angles like pi over 6, pi over 4, pi over 3, pi over 2, and pi to make an angle like 7 pi over 12 by adding or subtracting some of them from the others. One easy thing that will probably help you to do that is to translate all of them into the same denominator. So pi over 6 could be written as 2 pi over 12. Pi over 4 can be written as 3 pi over 12. Pi over 3 can be written as 4 pi over 12. Pi over 2 can be written as 6 pi over 12. And pi can be written as 12 pi over 12. So any of these that I can add together or subtract together in order to get 7 pi over 12, yeah, pi over 4 and pi over 3, or 3 pi over 12 and 4 pi over 12. If I added those together, I would get 7 pi over 12. So in this case, I'm going to rewrite this as sine of 3 pi over 12, which is pi over 4, plus 4 pi over 12, which is pi over 3. And I'll divide that by cosine of the same thing. Okay, and now I'm going to rewrite this using the sum and difference formula. So I'm just going to copy the right-hand side of this and paste it here. That'll be our numerator. Except, what is u going to be? U is going to be pi over 4, and v will be pi over 3. So I need to go pi over 4, pi over 3, and then pi over 4, and then pi over 3. Okay, and that's my numerator. And then the denominator will be what I get for the cosine formula. So the cosine formula looks like so. Paste it here. I'm going to replace u by pi over 4 and v by pi over 3. So pi over 4, pi over 3, pi over 4, oops, pi over 4, pi over 3. Okay, and then from here, what do? We just need to evaluate sine of pi over 4, cosine pi over 3, cosine pi over 4, sine pi over 3. Okay, so the two angles which are going to be relevant are going to be pi over 4 and pi over 3. So let me just do this in complete. I can be very complete with this problem. Here's pi over 4. Points at the point root 2 over 2, comma root 2 over 2. And then pi over 3 is bigger than that. Okay, and it points at a point which is like the x value is 1/2 and the y value is root 3 over 2. Okay, so we're going to use those points to determine what is sine of pi over 4, cosine pi over 3, blah, 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 blah. So all of the ones with pi over 4 are going to be the same, actually. Okay, so it's going to be root 2 over 2 times cosine of pi over 3. Cosine is the x value, so I'm getting 1/2. Then plus cosine of pi over 4 is root 2 over 2. Sine of pi over 3 is root 3 over 2. And then the denominator would be cosine of pi over 4 is root 2 over 2. Cosine of pi over 3 is 1/2. And then I get a minus sign. And then the Sine of pi over 4 is root 2 over 2 again, and then sine of pi over 3 is root 3 over 2. Okay, so if I wanted to simplify this up a little bit, we could get something like root 2 plus root 6 over 4 divided by root 2 minus root 6 over 4. And then we could rewrite that as, okay, dividing by this is the same as multiplying by the reciprocal. So I'm going to instead multiply times 4 over root 2 minus root 6. And I'll cancel the 4's. And I'll end up with root 2 plus root 6 over root 2 minus root 6. Am I done? We're never done when I ask that, are we? Okay, so let's ask ourselves, what is there still left to do? If the problem said simplify completely, there's a bit of a problem with where we're currently at. We need to rationalize the denominator. How do I do that for this one? Well, we learned how to rationalize things like 1 over the square root of 3. What do I do in this case? Yeah, multiply by the square root of 3 on the top and bottom, and you'd get something like root 3 over 3. So maybe we would want to try that. So we'll just multiply the top and bottom by the denominator. Let's see what happens if we do that. If you multiply the top and bottom by the denominator, then on the bottom we're going to FOIL, right? And we would get 2 minus root 12 minus root 12 plus 6, which would be 2 minus, oops, not 2, which would be 8 minus 2 root 3. So, okay, if I multiply the denominator times this guy, when I do the FOIL, I end up actually creating 2 additional square roots. Right? I end up creating 2 additional square roots. So at the end, if I multiply by this, the same thing on the bottom and top, just multiply by the denominator, I still have a root in the denominator. But there was a method that we learned which would prevent these middle terms from accumulating. Do you remember what it was?
So multiply by square root of 2 plus square root of 6.
Yes, you have to multiply by the square root of 2 plus the square root of 6. And that's called multiplying by the conjugate. So let's see how that works. Okay, multiply by conjugate. Okay, if you were wondering, what is the conjugate? A plus B and A minus B are conjugates. So if you have a minus, you just change it to a plus. If you have a plus, you change it to a minus. So in this case, I'm going to do multiply by square root of 2 plus the square root of 6 on the top and bottom. Now let's see what happens on the top. We're going to get root 2 plus root 6 squared. We'll do that later. On the bottom, what am I going to get when I FOIL? I will get 2 minus root 12 plus root 12, and then minus 6. Okay, so notice, by virtue of having a plus here and a minus here, the middle terms cancel out. The middle terms cancel out. Okay, so these ones cancel, and I'm left with just root 2 plus root 6 squared on the top, and on the bottom I have just negative 4. Okay, and if you wanted to FOIL that out, you would get 2 plus root 12 plus root 12 plus 6, which would be 8 plus 2 root 12 over 4, negative 4. And then 2 root 12 can become 4 root 3. So we get 8 plus 4 root 3 all over negative 4. Cancel 4, 4, 4. This becomes a 2, 1, and 1. And we're left with 2 plus the square root of 3. Okay? So, this is what I'm talking about when I say that Chapter A is not going to be directly examined on the final exam, but you need to know how to do the stuff from Chapter A, because if the problem said, okay, do tan of 7 pi over 12, simplify completely, this is the answer that I would want to see. Does that make sense? So unfortunately, there's no escaping Chapter A, even though you're not going to be directly assessed on it. Any questions on this one? Yeah.
Where does the negative go with that?
I probably made a mistake. Thank you. It should be, yeah, it should be negative and then minus. Thanks. Yeah, all the time I make silly errors like that when I'm like trying to, it's kind of hard to like talk about what you're doing while you're doing it, but what you're talking about isn't what you're writing. It's like if you were trying to read text and write something else at the same time. It's like your wires get crossed. Okay, thanks for pointing that out. Any other questions? Okay, so the take-home message for this one is, look, if you want to do tangent of a like sum or difference, you just do sine and cosine of a sum or difference, and you just apply the formulas. And I think all of this stuff, computing all of these, should be quite familiar at this point in terms of like go to the unit circle, do the angle, find the point, draw the triangle, etc. And then it's just some simplifying radicals, okay, which is annoying. Yeah, it's annoying, but I'm pretty sure you could do that. Maybe the one thing you might forget is how to multiply by the conjugate, but we just reviewed that, so now you're going to remember it for sure. Okay. Any final questions on this one, or another question from somewhere else in the content? Okay, then I'm going to go through these, and what I'd like you all to do is have your pencil at the ready to write down, okay, concepts that I say that you don't remember how to do, and the relevant section. Okay, so I'm just going to go through and list them off. So 1.1, coordinate plane, finding points, distance formula, midpoint formula. Let me know if you want me to slow down. Okay, graphs of equations, finding the height of the function by plugging in x values. Graphs of quadratics, okay. Then we had lines, equations of lines, point slope form, slope intercept form, parallel and perpendicular lines, okay. Remember the slope of a perpendicular line is like negative reciprocal, that sort of thing. Okay, modeling application. Oh, we didn't do that part, did we? Okay, then functions. What even was in the functions stuff? Let me look. Okay, you had to like plug things into functions. Okay, domain of a function. No square roots of negative numbers, no dividing by 0. Vertical line test. When is a relation a function or not? Okay, plugging into functions, right? How do we find f of -1? You just replace x by -1, right? And plug with parentheses. We always plug with parentheses, right? And then, okay, more domain. Geez, this was a long homework. Holy crap. Okay, graphs of functions. How do you get the graph of the function? And what is the relationship between the algebraic statement like g of 2 is equal to 4 or g of 2 is equal to 3 and the corresponding point on the graph, right? So being able to take statements which look like g of 2 equals -6, being able to graph the point, which would be, of course, the point like 2, -6 or something like that. Let's see, what else is in here? Okay, determining whether functions are equivalent to one another or not. All right, so that was functions. Okay, for real, can you chill out? So what else did we have? Next up was properties of functions, whether a function is increasing or decreasing or constant, continuous. Okay, whether a function is continuous. Then we had transformations of functions. Okay, that was a big one. Moving them up, down, left, right, squishing them, stretching them, reflecting them. Is that all we did? That's probably all we did. Okay, and then also the library of functions, which was, okay, all of those functions which we should know how to graph just on our own, like x cubed, square root of x, 1 over x, these sorts of functions which you should have sort of memorized. Okay, then came combining functions and compositions. So plugging functions into other functions, finding out the domain of compositions of functions was a sticking point, right? Because if we have something like f of g of x, right? F of g of x, then x needs to be in the domain of g, and whatever is the output of g of x needs to be in the domain of f. Okay, so that was a bit of a sticking point. Okay, also like finding like f of g of 2, okay, right? You plug 2 into g and then plug the output of that into f and find out what it is. So we had all sorts of stuff like that. Okay, then we moved on to chapter 2, where we studied quadratic functions. Okay, we learned how to factor quadratic functions. We learned the quadratic formula. We learned how to factor using grouping. So factoring something where the a value isn't 1 was a little more complicated, right? Then we also had things like completing the square in quadratic functions and things like that. Also graphing quadratic functions, okay? So making the parabola, whether it's stretched or moved left, right, or whatever, okay? We had this special form we would put it in called vertex form, right? It was like, okay, I gotta go back to my thing. It was like, vertex form was like x minus h quantity squared plus k, right? Or maybe a here also. Something like this was vertex form, where it told you exactly where the vertex was, namely hk. So, if I gave you something like x squared plus 2x plus 1, how would you get it into vertex form? Question for the class. If I gave you a quadratic that wasn't in vertex form and I asked you to put it in vertex form, what tool did we learn for that?
So minus b over 2 squared.
Yeah, we did it in office hours yesterday. It was completing the square. Okay, completing the square. Which actually this one's already completed, right? Because if you take 2, divide it by 2, you'd get 1. Square that, you get 1. It's already being added here. This is already a perfect square, actually. It would just be, so x squared plus 2x plus 1 is actually equal to x plus 1 squared. So in this case, now it's in vertex form. The k value is 0, the h value is -1. Okay, so that's completing the square. Let's see, what else? Polynomial functions, okay, of higher order. How many terms will they have? What will they look like? Will the ends go the same way, or will the ends go different ways? And what will the end behavior be? Will it be like this, or will it be like this? Okay, I feel like I'm doing a dance up here. More polynomial functions, I don't know, stuff like degree. What is the degree of a polynomial function? How do I know whether a function, if I look at it, is a polynomial or not? What is the graph of a polynomial function like? It's smooth and continuous, right? Then we had dividing polynomials, okay? Long division. Remember way back when we did long division with polynomials? We also had the rational zeros test, which told us if I have a polynomial, the rational zeros of that polynomial have something to do with the coefficients of the leading term and the tail term, right? Something to do with those coefficients and their factors, right? So in particular, one really useful thing that we learned, which will be useful if you go on and take calculus or other math classes, is factoring cubics, okay? Now, factoring cubics, generally what we did was we used the rational zeros test to guess one of the factors, used long division to divide it out, and then the remaining quotient was a quadratic, which we used quadratic formula or factoring on, right? So that was how we did factoring of cubics. Am I going too fast? Do we want to slow down, or anyone? Okay. So I hope you're writing down these things that you maybe don't remember. So then we had, what was next? Okay, rational functions. I promised Sully last time that we would talk about rational functions. We'll probably talk about that today, unless there's other questions. So rational functions are polynomials divided by other polynomials, right? And there was a big, there was quite a difficulty in graphing them, right? It was like a 8-step process or something like that, where we had to find the asymptotes, vertical and horizontal asymptotes. We had to find the zeros. We had to find the y-intercept. And we also had to determine the behavior of the rational function at the asymptote, right? So there was a question of, okay, if I have an asymptote, does the function go like this? Okay, does it look like this? Or is it the opposite? Is it like this? Okay, or are they both on top or both on bottom? Okay, it was a big question, which had to do with basically the multiplicity of the zero in the denominator and also the sign of the leftovers. Okay, so that was tricky. Then we talked about, well, we didn't really talk about oblique asymptotes. We talked about polynomial and rational inequalities. What was the main tool that we used to solve polynomial and rational inequalities? Maybe it would help if I wrote one out on the board. Something like this. What was the tools that we used to do a rational inequality like this one? Can I just multiply both sides by x minus 3? I would lose some information that way. What do I have to do instead? Maybe this will jog your memory. Yeah, test point. There we go. I'm going to do the test point method. I'm going to put the zeros of the numerator and denominator on the real line, and I'm going to pick a test point from each subregion. Okay, from each subregion. I know that the expression on the left-hand side can only change sign at one of these 3 locations. So it's going to have a uniform sign in each subregion. Okay, uniform meaning all the same. Okay, so that was rational inequalities and polynomial inequalities, the tool which we use for anything beyond a linear inequality is always the test point method. Okay, always the test point method. Okay, then zeros of a polynomial function. What even was it? Oh, we didn't do that. Okay. Oh, that's right, because that was just fundamental theorem of algebra, but in a really weird way. Okay. Yes, I remember why I skipped that. Okay, so then we had 3.1. What was 3.1? Exponentials, I think? Exponents? What? Why does it not? Oh, I guess it's probably because I made that homework or something. Let's take a look at it. Okay, find the exponential function which passes... Jesus, I cannot speak. The exponential function which passes through 2 points, okay? how do we do that? That was, okay, this is not an exponential function. This is a number, right? Okay, here we go. This is what I was talking about. Find the function of the form, blah, 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 that contains the given graph points, okay? This is a great question. We had it on one of our exams. Okay, then we have transformations of exponential functions, okay? So exponential functions that have been stretched, shifted, reflected, or whatever. Okay, so that was 3.1. And then we started talking about logarithms. Okay, so the thing with logarithms was they undo exponentials, okay? They're like how every mathematical operation has its inverse counterpart, right? Multiplication, we've got division to undo it. Addition, we've got subtraction to undo it. Exponentiation, we have logarithms to undo it, okay? And vice versa, right? You can also go the other way. So that was logarithms. So for each log equation, there's a corresponding exponential equation. So then we learned the log rules, like log of a product is the sum of the logs, okay? And so on and so forth. And then we also had the power rule for logs, right? That was the most important one. So in that vein, we had lots of problems where we would take a single logarithm and expand it as much as possible, or we would have many, many logarithms and try to combine them all into one, using those rules in one direction or the other. Yeah?
Can you do like some problems with like the natural logs?
Sure, problems with the natural logs. Like, okay, let me look at the log rules maybe, preview. So natural log specifically, or like other logs, or what?
Honestly, yeah, like anything is fine.
Okay, anything is fine. Then why don't we do an expansion problem? Let's do something like this. This was on one of our quizzes, I think. Or maybe an exam, I don't know exactly. Let's do it. Log of square root of x squared plus 9 over x plus 5. So let's try this one. So the goal, or the instructions, are to expand fully. Okay? So the first thing I notice is there's a division inside of here. What does division code as if we are to expand this thing? It becomes subtraction, right? So we get log of square root x squared plus 9, and then minus log of x plus 5. Okay, now we want to expand this some more, or am I done? Okay, we can expand more. What can I do? The square root, something I can do with the square root. What is it? You can bring it out how? As a 1/2. Okay, I can rewrite a square root as a 1/2 power. And I can use the log power rule to bring the power out, so it becomes 1/2 times log of x squared plus 9.
Could you have, I was going to ask just, can it be x plus 3? Because wouldn't that like solve the square root?
Okay, so the question is x squared plus 9 equal to x plus 3 or not? Who says yeah? Who says no? Who's too scared to answer? Okay. I think everyone is too scared to answer. Okay, well, if you see something like this and you're not sure, okay, how can you check it? Well, you know you could disprove this using one of the techniques that we learned, which is namely, if I can find one number for which this is not true, I'll be done. Watch this. Let's try x equals 1. Is the square root of 10 equal to 4? No. See, we've disproven this identity. Okay, so this is not an identity. Here's why. Basically, a square root is a nonlinear action. Am I out of time, or do I have time still? 10 minutes. Square root is a nonlinear action, which means that this will never be equal to the square root of x squared plus the square root of 9. Can't fault you for believing that, though, considering how many linear actions we've seen through the course of this class. But in this case, what would we need to do? If this was true, okay, another way you could see that it's not true is by squaring both sides. If you square the left side, you get x squared plus 9. If you square the right side, you get x plus 3 quantity squared. And this will help you to see why this shouldn't be true. Because what would I need to do to multiply on the right side? I can't just bring this down here, can I? What do I have to do? FOIL, right? And if I FOILed, I would get x squared plus 3x plus 9. Now you can see why they're not the same, right? Okay. So what I wanted to illustrate here is not to just like painfully take you through your mistake here, Connor, but rather to show you all what you can do when you feel like maybe something's true, but I'm not really sure. Like you can assess on your own to decide whether you think it's true or not via one of these two methods, right? You can rearrange the equation and see, okay, that doesn't seem right. Or you can try some test points and see if it's true for the test points. In fact, the only point that this will be true for is x equals 0. That's the only time that this will be true, right? Okay, so that's just tools for you to use when you're on the exam and you can't ask me questions like that. You can always ask yourself and try to answer your own question. Okay, but can we take this any further? How about this? Valid or not valid? I'm seeing shit. Hey, Jesus. I don't know why. I just can't speak today or ever, I guess. I'm seeing heads shaking and heads nodding, so we should probably talk about it. It's actually not valid, and here's why. If I want to bring a power out, okay, the power needs to be on the entire thing, okay? Something like this, then I could bring this power out, okay? But this power is only on the x squared, so I actually can't take it out like this, okay? I can't take it out like that. So this is not valid. Is there anything else we can do, though? Or am I just done? Well, the only thing that I can think of to do would be to try to factor this, okay? Would be to try to factor this. And then if you were able to factor it, then you could use the product to sum rule, which would say that this would become like log of this thing plus log of this thing. But I actually don't think that I can do that, because this polynomial does not have does not have real roots, right? The roots of this are complex. So this can't be factored. At least it can't be factored using real numbers. So I think this is where we would stop. Okay? So that's an example of the log stuff. Does that satisfy you, Connor, or you want to see more?
No, I got it.
Okay. So that was logs. Let's see. Let me go through the rest really quickly. So the rest of this stuff is more recent. So then we learned, okay, exponential log applications. That was basically half-life and doubling time. Then we had solving exponential equations. Okay, so when the thing that we want to get is inside of an exponent, we got to use logs to get it out. When the thing that we want to get by itself is inside of a log, what am I going to use to get it out? Exponents, right? Or exponentiation, I guess, as a process. Okay, so we saw lots and lots of log applications. And then we moved into chapter 4, which is where trig started. Trig started with learning angles, degrees, radians, terminal side, initial side, standard position, coterminal angles, reference angles, and then 4.2, 3, 4, what did we learn? We learned how to do sine, cosine, tangent, secant, cosecant, and cotangent. We learned some Pythagorean identities. We learned, probably be easier if I go back to my notes here and I can just look at what we learned. Okay, then we learned inverse trig, okay? We learned arcsine, arccosine, arctangent. We learned how to do the graphs of the trigonometric functions like sine, cosine, and tangent. And also how to stretch them, shift them, and do all sorts of different things to the graphs. We learned how to tell where the trig functions are positive, ASTC. All students take calculus. We learned how to do triangles like 30, 60, 90 triangles, 45, 45, 90 triangles. And then we learned how to do, let's see, that was pretty much it in chapter 4. Chapter 5, 5.1 was all about trigonometric identities, okay? Reciprocal identities, quotient identities, Pythagorean identities, and even an oddness of sine and cosine, even an oddness. And during this, we learned how to verify and disprove trigonometric identities. Namely, to disprove, you got to find one input for which the identity is not true. To prove, we have to reduce both sides to an obvious equivalence or another known identity, like a Pythagorean identity or something like that. We also learned the sum and difference formulas, which we saw in play today. We learned the cofunction identities, namely sine and cosine look exactly the same, but moved over and reflected a little bit. We learned double and half angle formulas for power reducing of sine squared to like something like cosine of twice the angle. And we also learned trig equations. That was the last thing that we did. Well, second to last, I guess. But it's the last thing that will be on the exam because you know the exam questions come from the homework, and the last homework is 5.5. So no 5.6 or 6.1 on the exam. So trig equations was all about finding all of the inputs which cause a trigonometric equation to be true. And we learned how to do this in many, many settings. So the first and most simple setting was just to do something like sine equals cosine, or to do something like sine of x equals 1/2, okay? Sine of x equals 1/2. And then we also learned how to do it in more complicated settings, like where we have to first do a little bit of rearranging, or where we first have to do a little bit of quadratic form stuff. So, okay, I hear you all packing up. Give me 1 second, okay? I just want to remind you, okay, that we had no quiz 7, okay? But I had an anonymous survey response which said that they wanted to have a quiz 7 in order to improve their quiz score, and I thought that's fair. So what I did was I posted an optional assignment onto the Blackboard, okay? If you complete the optional assignment, I will grade it, and I will put that in place of your quiz 7 score, okay? Yes? It'll be due the day of the final. So if you do that, I'll give you a quiz 7 score. If you don't do that, then I will just take your quiz score to be the best 4 of 6. Okay, so that way you can have both options. And yeah, that's it. I'll see you all tomorrow.